Hello everyone, welcome back to the channel. I hope you all are doing great. So we were discussing about the previous year questions of the CSIR NET exam, and in that the chapter we were discussing was the kinetics. Right, so already 4 of the parts of this unit we have discussed. If you have not watched playlist I have made on the channel, you can check that, or I'll provide the link in the description. Even from that you can get the access to it. So let us begin with the part number 5, in which the remaining questions we are gonna cover it. Okay, so let us begin with the solutions. So these are the questions from the CSIR June exam conducted in the year 2023. Before this, all the years questions, that is from 2011 to the year 2022, all the questions we have discussed in the previous 4 parts. Okay, so this question, it says that in the Jablonski diagram, which is shown as below, the initial excitation, it takes place from the singlet ground state to the second singlet excited state, which is from S0 to the S2. Match the processes of the events which are marked as A, B and the C. So this is your, let me just highlight, this is the process A, this is the process B, and this is the process C, they are saying it. So the A process in that, so let me just draw this Jablonski diagram firstly. This is from the S0, this is, here is S1, and here is this S2. So from the S0 to the S2, this excitation of the molecule has taken place. The A process is, here are 2 of the triplet states that are present. Here it is T1 and this is the T2 state. So the first A process that is taking place, in which this particle is coming from the S1 to the T2 state, it is coming. So here you see the molecule is coming from the one of the state to the another state. So this process, it is called as the inter-system crossing, right? That is called as ISC. In the B process, the particle is returning from the T2 to the T1. So here the states are remaining the same, and this is the radiative process. Generally the radiative processes are denoted like this. This is radiative processes, and this denotes like this, that you are having, this is the non-radiative process. And the radiative processes, we are having only the two, that is the fluorescence and the phosphorescence. If between the same spin states this transition is taking place, that is fluorescence, and if it is between the different spin states, that becomes the phosphorescence. Okay, so here now it is from the T2 to the T1, which means the same spin states it is taking place. So the B process, it will be called as the fluorescence. Fluorescence. Okay, and in the next step, what is coming, this particle is returning from the T1 to the S0 state, it is returning again. This is your radiative process, and the state of the change of the spin states, it is taking place. So this is called as the phosphorescence. So these are the processes. A is ISC, which is intersystem crossing, B is fluorescence, and C is the phosphorescence. So this is the C1. So ISC, fluorescence and the phosphorescence, the correct answer is the option D in this case. Okay, next is this question. The transition state theory was developed to explain the empirical Arrhenius expression for the rate constants for a non-linear transition state with n number of atoms, the effective number of the vibrational degrees of freedom, which is used in calculating the vibrational parameter. So according to the transition state theory, we have that the reactant molecules is in equilibrium with the transition state, right? This equilibrium is present. Now they are saying it is the non-linear transition state has been developed over here. Now to discuss about this transition state theory, you two of the approaches you use, thermodynamical and the statistical approach, and in statistical approach you find the partition functions. So for the non-linear molecules, the number of the vibrational degrees of freedom, you have it, that is 3n minus of the 7. In generally we have, it says the number of vibrational degrees of freedom is 3n minus of 6, but in the transition state theory there is presence of one loose vibrational degree of freedom, so that is subtracted from this. Okay, so it is 3n minus of the 7. If it would have been the linear, in that case number of vibrational degrees of freedom would have been 3n minus of the 6. Okay, so now it is the non-linear one, so 3n minus 7, that means the B option, it becomes the correct answer. Okay, next is this question. It says an acetone undergoes the photodissociation upon the absorption of 330 nanometers of the light. Exposure of a gaseous sample of the acetone to the radiant power of 20 milliwatt at 330 nanometers for a period of 3 hours result in a photodissociation of 75 micromolar of the moles of the acetone. What is the quantum yield? So quantum yield, it is defined as amount of the reactant reacted, amount of the reactant that is dissociated upon the amount of the photons, amount of the photons. Now how do we find this amount of photons? Amount of photons, this is equal to energy observed, energy that is observed upon the energy of the 1 mole of photon, 1 mole of photon. This we take it as E observed upon this energy of 1 mole of photon, we write it as 12 upon the lambda in the centimeters. Okay, so now here just substitute these values now and find the value of the quantum yield. So here it is shown that the dissociation of this much amount of the acetone is taking place, which reflects that the amount of the reactant which is dissociated is given to us. This value is 75 micromoles of it, right? And E observed, that we have to find it out. This is power is given to us and time period, it is 20 milliwatt for a span of 3 hours, right? So power into the time, so it will become 20 into 10 to the power of minus of 3. This will become the watt, which is joule per second only, into the time, which is of the 3 hours, so converted into the seconds, 60 minutes and 60 seconds. So this is converted time period in the seconds. So this second and per second, it is getting being cancelled out. You are getting the energy in terms of the joules upon 12 upon the wavelength, which is 330 nanometers. So it becomes 330 into 10 to the power of minus of 7. This is in the centimeters. Okay, so these are the values you will be getting. So on solving all of this, we will be getting the value as 0.000594. This is the value we will be getting. Now to find the quantum yield, just take the ratio of the amount of the substance that has dissociated to this value. So here we will be having the phi value as 75 into 10 to the power of minus of 6 upon the 0.0000594. On solving this, the value we will be getting it as 0.126, which becomes 1.26 into 10 to the power of minus of 1. So this is gonna be our quantum yield. Okay, so the answer is in the option B, we are having it, right? Moving upon to the next one. This question is that it says a reaction, it follows the rate law, in which minus of dA by dt, this is giving us the a raised to the power of 2 of it, which means it is the second order reaction. Starting from an initial concentration A naught, the time taken for the concentration to reduce to A naught by the 4, namely the quarter life of the A. So the reaction order, we are writing it minus of dA by dt of the A, this is equal to K into the A square. That means the reaction is following the second order kinetics, right? So for the second order, the integrated rate law expression is 1 by A minus the 1 by A naught is equal to the Kt. Now the remaining concentration has reduced to A naught by 4. So A's value it will be A naught by the 4 minus of 1 by A naught. This is equal to Kt quarter of it. So this become 3 by the A naught, that is equal to Kt quarter of it. So from here the T quarter, this is equal to 3 by A naught into the K. This is gonna be the value. That means the option D, that is 3 by A naught into the K, it becomes the correct answer. Okay. Next one is this question. So the rate of the acid catalyzed reaction in the aqueous solution follows the rate equation given by this rate expression. Three of the ionic species here are involved in it. That is your X positive, Y2 negative, and we are having is H positive. The rate constant for the reaction at ionic strengths of 16 moles per liter and 9 moles per liter are K1 and the K2. The values of the log of K1 by the K2 in the units of the Debye-Huckel constant Bs. So this question is belonging to the primary salt effect, according to which when three of the ionic species are present, we write the expression of the rate constant like log of the K1, this is equal to log of the K0 plus of the 2b. Why b? Because Debye-Huckel constant and in terms of the b over here, so that is why b we are using. Now here three ionic species are involved, so the rate will be this, it includes the Za into the Zb plus of the Zb into the Zc plus of the Zc into the Za, this into the root of the ionic strength. Here Za, Zb and Zc, these are the charges present on the ions. These are charges on the ions. Okay, so now it's given when the ionic strength is 16 moles per liter, the rate constant is K1. So that you can write it as log of K1 and substitute the values of the charges and the ionic strength. It becomes 2b. Now Za is X plus 1 is there, so it will be plus 1. Zb charge is minus of 2, so that we can substitute plus of the minus of 2 into the plus of 1 plus of the plus 1 into the plus 1 into the root of ionic strength is 16, so this we have substituted, so this becomes equal to log of the K0 plus of 2b times, this will become minus of 2 plus of the 1 into the 4, so this becomes 2b into the minus of 3 into the 4, that is 24b, negative sign, and here this log of the K0 is as it is. So this is the value of the log of the K1 we are having it, right? Now the next is ionic strength is of 9 moles per liter. In that case, log of the K2, this will be equal to log of the K0 plus of the 2b times the Za, Zb plus of the Zb, Zc plus of the Zc into the Za into the root of the ionic strength. Now ionic strength is 9, so that we can substitute plus these charges which were, it was plus 1 minus 2 plus 1 into the minus of 2 plus of the minus of 2 into the plus of 1 plus of the plus 1 into the plus 1 into the root of the ionic strength which is of the 9, right? So on solving this, the value will be log of K0 plus of 2b times, this will become minus of 3 into the 3, so this becomes 9 2s are 18, that is minus of the 18b. So this was log of K0, that is equal to log of the K2. So log of K1 and the K2 value you have calculated it. So we need is the ratios of these two, because log of K1 by the log of K2 value is being asked. So subtract both of them. Log of K1 minus the log of K2. This will be equal to log of K0 minus of the 24B minus of log of the K0 minus of the 18B. So this log K0 gets cancelled out. It becomes minus 24B plus of the 18B. That means it becomes the minus of the 6B. So this is the value of the log of K1 upon the K2. So this is the answer we will be getting. So here if I'm seeing in from the options, you can see none of the options is matching with the given with this answer, and nor you can see that the Debye-Huckel constant B, in terms of that the answers would have been given, and that is not given in any of the options. So when this question was asked, that was in the paper that was for the June exam that was conducted in the December, and this 2023 June exam, a merged cycle, this paper was conducted, and in that this question it was omitted from that because none of the options was correct. So the correct answer will be the minus of 6p only. Okay. Next one we are having is this one. So this is from your December 2023 exam. According to the Arrhenius equation, the plot that correctly describes the temperature dependence on the rate constants. So this is from the Arrhenius equation. Arrhenius equation, we have that rate constant K is equal to A e raised to the power of minus of the EA upon the RT of it. EA upon the R into the T. So if I see the values, if I am increasing the temperature, this is RT. So if I am increasing the temperature, the value of 1 by T it decreases, right? Or we can say the value of minus of EA, or this EA upon the RT value, it's gonna increase because negative sign it has been placed over here. So 1 by T it was decreasing, and this negative sign it shows that this value it is increasing. So if I make a plot that is for the this rate constant K value, it will be increasing in that case, right? So here we can see, if I see a plot that is for the temperature versus the rate constant, that implies if temperature it increases, the rate constant value it is gonna increase in that case. But here the plots are for the temp K versus the 1 by T, which you can see 1 by T it is decreasing and the rate constant value it is increasing in that case. So if 1 by T it is increasing, rate constant K it is gonna decrease in that case, right? So here if I see it, that in the options in A, if you see, with the increase in this 1 by T value, the value of the rate constant K it is decreasing, and that is exponential decrease as per our equation, that is K is equal to A times e to the power of minus of EA upon the RT. So 1 by T value, if you are increasing, this exponential term e raised to the power of minus of the EA upon the RT, this value it is decreasing in that case, which implies that the rate constant it is decreasing. This is when 1 by T we are increasing it, right? So this is what you are observing, an exponential decrease in the value. So the option A it becomes the correct one. So make sure it is K versus 1 by T and not the K versus the T. With the increase in temperature, rate constant is increasing, but with the 1 by T it's gonna decrease over here. Okay. Next is this question. It says two reactions, they have the same pre-exponential factor, but their activation energy of the first reaction is lower than that of the second reaction by 5 kilocalories per mole. What it implies? The first reaction is lower. So EA one that I am having, this is 5 kilocalories per mole lower than that of the second one, which implies the difference between these two, activation energy of the second reaction minus of the first one, the difference between them it is of the 5 kilocalories per mole of it. How can we write the rate expressions? K1 it will be A times e raised to the power of minus of EA1 upon the RT, and the rate constant K2, this will be equal to same pre-exponential, so A into e raised to the power of minus of the EA2 upon the RT of it. So they are asking us the ratios of the rate constant of the first and the second reaction is, that means K1 upon the K2 value is being asked. That becomes A times e raised to the power of minus of the EA1 upon the RT, and here it will be A into e raised to the power of minus of EA2 upon the RT. This gets cancelled out. This will become e raised to the power of EA2 minus of the EA1 upon the RT of it. These values are given to us, which is the difference between two is 5000 calories per mole, and the R value in terms of calories, it will be 2 calorie per mole per Kelvin, and the temperature, it is given to us as 298 Kelvin, right? So this value, just you have to find this out and you will be getting your answer, right? So on solving this, the answer we will be getting it will be close to the option which is 4650. So this is gonna be the ratio between these two. So the option A, it becomes the correct answer. The exact value, if you wanna see it, that is gonna be around 4628. So the closest answer match is the option A only in this case. Okay. Next one is this question. It says that the isomerization of cyclopropane to the propene, it follows the Lindemann mechanism and is carried out in high pressure. High pressure limit, it is being carried out. The ratios, so firstly it is the Lindemann mechanism. So what is the Lindemann mechanism? We have two of the molecules A and A. They are activated with the rate constant K1, giving us one of the activated molecule plus of the A, and the backward direction of it is K inverse, and in the second step this A star with the rate constant K2, this gets converted into the product P. The rate expression for this we get it K1 into the K2 into the A square upon the K inverse of A plus of the K2. This is what it is given, what the value of the rate you will be getting. Now it is at the high pressure limit, at the high pressure, which means the value of the K inverse of A, it is much greater than that of the K2, right? So this condition we can apply it, that the rate value, it will be K1 into the K2 into the A square upon the K inverse of the A. This is what we will be getting. So with this A1 of the A, it will get cancelled out. We will be getting the rate as K1 into the K2 into the A upon the K inverse. This is gonna be there. Now the next statement, it says the ratios of the rate constant of the activation to the deactivation step is 10. So the activation step rate constant is K1, and for the deactivation the rate constant is K inverse, right? So the first step, that is the activation. This is the activation, and the reverse of it, it is deactivation. Deactivation, and the third step, this is called as the decomposition. Okay, so K1 to the K inverse ratio, it is given to us as 10, and that of the product formation to the deactivation step is 50. That means K2 upon the K inverse value, this is equal to the 15. Given that the effective rate constant is this much, 150 second inverse we are having, the rate constant for the deactivation step is, so the exact value of this K inverse, it is being asked, and the effective rate constant, that is this one K effective, it is K1 into the K2 in upon the K inverse, this value is given, which is 150 second inverse. So this is the effective rate constant after imposing the condition. So now K1 by the K inverse ratio and K2 by the K inverse ratio, that is given to us, that we will be making use to find the value of K inverse. So K1 upon the K inverse, this was 10, and K2 upon the K inverse, this was equal to 15. And the overall effective rate constant is K1 into the K2 upon the K inverse. This is equal to 150 second inverse. So K1 value in terms of the K inverse, it will be equal to 10 times the K inverse, and K2 value in terms of K inverse, it is gonna be equal to 15 times the K inverse upon the K inverse. This is equal to 150. So from here one of the K inverse will get cancelled out. So it becomes 150 K inverse. This is equal to 150 only. This is equal to 150, which implies the value of K inverse is 150 upon the 150, that is equal to the unity. So this is the answer for the K inverse. So that is given to us in the option B. Okay. So the next question now we are having is, it is this one. So this is from your June exam conducted in the year 2024. The question, it says the reaction A to P, it consists of the following three elementary steps with their respective activation energies. So A to the I, this is with the activation energy EA1. This we can say that the rate constant for it is K1. This second step, that is I to the A, which is with the activation energy EA2, and the third one is also given the activation energy of the overall reaction. For that we need to find the overall rate constant of the reaction. Rate of the reaction firstly we will be finding. So the rate of a reaction, it is dependent upon the slowest step of it, and in the brackets it is already shown that these steps are the fast and this is the slow step. The slowest step, it will include, that is K3 times the I. This is gonna be the rate expression. Now here the I value that I'm having, this is the intermediate, so we have to find its concentration so that we can substitute in the rate expression. So for that we are gonna apply the SSA over the I. So on this side we are applying it SSA on the I. That means di by the dt value, it will be equal to the 0, or we can also make use of the equilibrium approximation in this, because here the reaction is A to the I, this is given, and I to the A, this is with the rate constant K1, and this is with the rate constant K2, and both of this, they are the fast step. So equilibrium it is present. Why this equilibrium? Because in the first step I was being formed and in the second it was being consumed. So these are the fast steps and the equilibrium will be present, having the rate constants K1 and the K2 of it. So this fast process, whenever we are having an equilibrium as a fast one, so in that case equilibrium approximation can be used. Equilibrium approximation is used. So for that the value of the rate constant to the, of the forward to the backward direction, this is equal to the product concentration upon the reactant concentration. So from here I value, this will be equal to K1 times the K2 times the A concentration. So this is gonna be the I value that you can substitute in your rate expression. So overall rate, it will become, it was K3 times the I, that means it will become K3 times the K1 into the K2 into the I of it. This is gonna be the overall rate expression, and the K overall, that is the overall rate constant, this is equal to K1 into the K3 into upon the K2 of it, right? So to find the overall activation energy, K value is K1 into the K3 upon the K2 of it. This directly you can also write if you know it, but I'll be showing you the complete this derivative part of it. So how we can do this? Take the ln of the K overall. This will be equal to ln of the K1 plus the ln of the K3 minus of the ln of the K2. Differentiate it with respect to temperature. With respect to the temperature, it will become d ln K by the dt. This is equal to d ln of the K1 upon the dt plus of the d ln K3 upon the dt plus of the d minus of d ln of the k2 upon the dt of it. Now according to the Van 't Hoff equation, d ln k by the dt, this is equal to Ea upon the RT square. So that you can substitute. So it will become Ea, which is the overall, upon the RT square. This is equal to Ea1 upon the RT square plus of the Ea2 upon the RT square minus of the Ea1 plus of the Ea3, it was there, minus of the Ea2 upon the RT square. So on solving, overall activation energy, overall it is equal to Ea1 plus of the Ea3 minus of the Ea2. So this is gonna be the overall activation energy and the complete derivation part of it. So directly also you could write this, that K was equal to K1 into the K3 upon the K2. So the one that are in the multiplication, their activation energies addition we have to do it, and the one which is in the denominator, that we have to subtract it. This is the direct you can use it. Okay. So the answer becomes the option Ea1 plus Ea3 minus of the Ea2. Option D, it becomes the correct answer in this. Okay. Next one is this question. Statement based it is there. It says the correct statement about the pre-exponential factor in the Arrhenius equation. According to the Arrhenius equation, rate constant K is A into e raised to the power of minus of the Ea upon the RT. This is the pre-exponential factor. The first statement, it says that it is your dimensionless quantity. So is it correct or not? This exponential power that I am having, this is unitless or the dimensionless. This is dimensionless. Okay, but this k value that you are having, this is equal to the a. That means the a, it is having the units of the k only, right? Based upon the what order kinetics we are having, this k units are gonna be varying. So k units and a units are the same only, so it is not the dimensionless. It is not dimensionless. Okay, e raised to the power of minus of a by rt is there. This factor, it is dimensionless. Okay, next statement, it says it is necessarily has the second inverse in its dimension regardless of the order of the reaction. This statement, if you see, the rate constant, suppose it is of the zero order kinetics if we are having, in that case the units of the rate constant, it is gonna be equal to mole per liter per second, and this only is gonna be the units of the A also, right? If I have the first order, so in that case the units of the rate constant is second inverse, and that will be the units of the pre-exponential factor also. In the second order, if you see, the units are gonna be mole inverse liter per second of it. Same goes for the any order of the reaction, you can write this. So as per the statement, it is necessarily has second inverse in its dimensions regardless of the order of reaction. This statement is the true, because in the C0 order, you see, second inverse it is present. For the first order also second inverse term is present, and in the second order also the second inverse term it is present. So irrespective of what the order of reaction it is there, the units of this a pre-exponential factor, it contains the second inverse dimension. So this statement is the true one. Okay, next one also, you see, it does not necessarily have the second inverse in its dimension, so this is the reverse of it, so becomes the incorrect. Fourth statement, it has a concentration in its dimension regardless of the second order, regardless of the order of reaction. So this is not the true, because in the first order, if you see, only the second inverse term is present and concentration term it is not present in its dimensions, right? So this again becomes the incorrect. So B is the correct statement in this case. Okay. Next is this one, the order of a reaction which is going through the A to the P is 2 when the concentration of A is small, and at the higher concentration it goes to the 1. The mechanism of the reaction is. So we know that the unimolecular reaction, for this if you see the mechanism that we have, it is A plus of the A. This is in equilibrium with the A star plus of the A. This follows the rate constant K1 and the K inverse, and the A star to the product P. This is with the rate constant K2. The rate expression for this that I have, it is K1 into the K2 into the A square upon the K inverse of the A plus of the K2. This we have, this we already do this in the theory part, right? So if I take this at the low concentration, which means K inverse of A, it is less than that of the K2. So in this case the rate expression, it will become K1 into K2 into the A square upon the K2 value. So this K2 gets cancelled out, rate it will be K1 times the A square, right? This is what you are getting. So with respect to the concentration of A, this is raised to the power of 2. That means at the low concentration the rate is of the second order, right? Whereas for the higher concentration, it will be, we will be observing at the higher concentration, that is K inverse of A, it is more as compared to that of the K2. So rate it will be equal to K1 into the K2 into the A square upon the K inverse of the A, right? So this one of the A will be getting cancelled out, so the rate it becomes K1 into the K2 upon the K inverse into the A. So rate is proportional to the A's concentration raised to the power of 1. So R is proportional to A to the power of 1. That means it is following the first order kinetics. So this is the mechanism. So from the statement also you see it is second order when the concentration it is small, and it is at the higher concentration the order changes to the unity. This is what is happening at the higher concentration the second order, and at the lower concentration it is of the second order, and at the higher concentration it is following the first order kinetics, right? So this is gonna be the correct mechanism in which A plus A is in equilibrium giving the A star plus of the A, then the A star gives the product B. The option C, it is shown this mechanism, so C will be the right answer in this case. Okay, next one is this question. The rate constants for a bimolecular reaction according to the collision theory is given by E naught is related to the activation energy of the Arrhenius equation as, so this is from your Gardiner equation, with which the rate constant K is equal to A into T to the power of M E raised to the power of minus of the E naught upon the RT. According to this, the EA value, that is the activation energy, this is equal to MRT plus of the E naught. This is the value. So here M is the power of the temperature that we are having it, power of the T. So in the given expression of the rate constant K, this is of the collision theory, it is Na into 8 kBt upon the pi mu. This is raised to the power of half of it into the sigma into e raised to the power of minus of E naught upon the RT. So here if I see temperature is raised to the power of half of it in this case, which implies activation energy EA, it will be equal to, now M here is the power of T, so that is half into the RT plus of the E naught. So this is gonna be the activation energy, right? E naught plus of the RT by the 2, that means the option D, it becomes the correct answer. Okay, moving upon to the next one. This question, it says the fluorescence of a is quenched by 10% in the presence of 10 millimole molar of the B. So what is happening? The molecule A you are having, its fluorescence is being quenched by the other molecule, that is the B, whose concentration is this much. So A is the molecule which is showing us the fluorescence, and B is the molecule which is the quencher, right? So now here the concentration of B it is given. If the fluorescence lifetime of A in the absence of the B it is 5 nanoseconds, so that is the fluorescence lifetime, that we denote it as tau F. This is defined as the ratio of 1 upon the Kf plus of the KIC plus of the KISC. This value it is given to us as 5 nanoseconds. The rate constant for the interaction between the B and the photoexcited molecule A is. So that means they are asking the rate constant for the quenching, because when A is in coming in contact with the B, this activated molecule you can say it is coming in contact with the B. So here the process that is taking place is the quenching, right? So the rate constant for it is suppose the KQ it will be there, right? So now if I write the value of the quantum yield, in the absence of the quencher, in that case the value it's gonna be Kf upon the Kf plus of the KISC plus of the KIC. This is gonna be the one. This is the quantum yield of fluorescence in the absence of the quencher. Now if you have the presence of the quencher, in that case the quantum yield value that we obtain it is equal to Kf upon the Kf plus of the KISC plus of the KIC plus of the KQ, which is the quenching process rate constant, into the amount of the quencher, which is B in this case, right? So if I take the ratios of this, so this is basically from your Stern-Volmer plot, in that you define the ratios of this quantum yields, that is in the fluorescence in the absence of the quencher to that of the quantum yield of the fluorescence in the presence of the quencher, right? This will be equal to, so in the absence it was Kf upon this, so 1 upon the Kf plus of the KIC plus of the KISC, this it will become, and in the numerator we will be having the value of, that is of the presence, it will become Kf plus of the KIC plus of the KISC plus of the KQ times the amount of the quencher, right? This KQ amount they are asking us to find this out. So now we are having this quantum yield in the absence and in the presence. This becomes equal to Kf plus of the KIC plus of the KISC plus of the KQ times the B upon the Kf plus of the KIC plus of the KISC, that we can write it as 1 upon the 1 plus of the KQ times the B upon the Kf plus of the KISC plus of the KIC. This is gonna be there. This is equal to 1 plus of the KQ times the quencher's amount, and this 1 upon the Kf plus of the KISC, this is the lifetime of the fluorescence, that is this tau F, right? So now this value which is of the tau F in the absence, quantum yield in the absence and in the presence. So if in the absence of it is 100%, suppose it is there, now in the presence of it they are saying that this process gets 10%, it is getting being quenched, so the remaining fluorescence yield it is gonna be 90%, right? So this value it is equal to 1 plus of the KQ times the B into the tau F of this. Okay, so this it will become 10 upon the 9 minus of the 1. This is equal to KQ. This we have to find it out. Quencher's amount it is given to us, that was 10 millimolar of the B. So it was 10 millimolar 10 raised to the power of 3, and the tau f value that is given to us as 5 nanoseconds. So it will be 5 into 10 to the power of minus of the 9. This is what is given to us. So you can just solve this. It will become 1 by the 9 upon the 10 raised to the power of minus of 3 into the 5 into 10 raised to the power of minus of 9. This is gonna give us this KQ value that we will be getting it as 2.2 into 10 to the power of 2.2 into 10 to the power of 9, the value you will be getting it. So this is the value of the KQ. Okay, so I hope it's clear how is the process taking place. So you were having the fluorescence technique, you were carrying it out first time in the absence and then in the presence. When in the absence you were having the relaxation time, it is given to us, so and the quantum yield value we know, so that we have taken, and in the presence how much fluorescence quantum yield we will be having, that we took it. Then we took the ratios of this, the amounts it were known to us, and then we just substitutions were made and the KQ value we could easily find this out. Okay, so now moving upon to our next question, that is this one. So this is from your latest paper that is conducted in the June 2025. The question, it says the activation energy and the enthalpy change for the reaction which is H2 plus the I2 giving us the 2HI are this and this. Okay, so the reaction is H2 plus the I2 giving us the 2HI. Okay, for this the activation energy value, it is 167 kilojoules per mole, and the enthalpy, that is delta H, it is minus of the 8 kilojoules per mole, which shows that this reaction, it is exothermic in the nature, because delta H value we are having it as the negative. If we draw a reaction plot for this, it's gonna look like this. Here it's gonna be the energy and this is the reaction progress. So here I am having the H2 plus the I2. This is with some activation energy. This is giving us the product value P, which is my HI, right? So the activation energy in this case, this is the one from this to this level, right? This is the activation energy for the formation of the HI. This value, it is 167 kilojoule per mole of it, and the enthalpy, which is the difference between this level and this level, this gap value we are having it as, it is 8 kilojoules per mole of it, right? Now they are, next statement they are saying is, assuming that the pre-exponential factors of the production and the decomposition of the HI to be the same, the correct options is, okay, so the forward reaction, it is of the production of this, so this activation energy of the production of the HI, this was equal to 167 kilojoules per mole. But now for the decomposition of it, for the decomposition it's going in the backward, that is from HI we will be getting is H2 plus the I2. So for that, this is the total activation energy which we have to provide it, so that is gonna be 167 plus of the 8, right? That is gonna be 175 kilojoules per mole. That implies the activation energy for the production, it is less, but for the decomposition of it, it is more. This is what we are getting. Based upon this, the statements have been given. Let us have a look to that. So rate constant values also they are saying. So Kp will be the one that is for the production, A times e raised to the power of minus of the EAP upon the RT, and for the decomposition it is A into e raised to the power of minus of the, this is for the decomposition upon the RT. Now about this, the statement it says Kp and Kd have the same temperature dependence. Is it true or the false one? So we have to find us the correct statement in this now. So Kp and the Kd, does they have the same temperature dependence? So the answer is no, because activation energies are here different over here, right? That means their dependence on the temperature, it basically means if you are increasing the temperature, suppose this reaction which is of the production, you are carrying it initially at suppose 298 Kelvin, and then you change the temperature to the 10 degrees centigrade, you are increasing, so 308 Kelvin it is there. So if the rate constant value change that we will be getting, that will be at K 308 Kelvin upon the K 298 Kelvin for the production, this process when you are carrying it out. And for the other one, that is for the decomposition, this same process you repeated, that is at 300 Kelvin you carry it out, and that at the 298 Kelvin. This ratios you take it, these are the rate constants for the decomposition. So their dependence on the temperature is being basically asked. So here more is the activation energy, basically more is the effect of the temperature on the ratios of these rate constants. More is the activation energy, more is the effect of the temperature, more is the effect of the temperature, which means for the decomposition, the rate constants that I am having, this is gonna be more as compared to the production one, because we have seen that activation energy for the decomposition it is more as compared to that of the production, which means their dependence on the temperature it is not gonna be the same, right? Next statement, it says Kd changes more rapidly with the temperature than the Kp. This statement is the correct, because Kd, when you are taking this ratio change, that is at two different temperatures, having the, due to the fact it is having the more amount of the activation energy, so more effect of the change of the temperature you will be observing in their rate constants ratio. Okay, so B will be the correct answer in this case, right? Next question is this one. It says for a reaction which is K plus the Br2 giving us Kbr plus of the Br, the rate constant is described by this. Choose the correct option regarding the activation energy and the pre-exponential factor, where AE it is obtained from the experiment, and AT, that is the pre-exponential factor which is obtained using the collision theory. So this question it is from the harpoon mechanism. Harpoon mechanism. According to this, the steric factor that you have, this is the steric factor, which describes the ratios of the pre-exponential factor that is obtained experimentally to that which is obtained by the collision theory. Okay, for this one, the rho value that you have, that is of the steric factor, it is greater than the 1. Okay, and in that means AE by the AT ratio that I am having, this is greater than the 1, so AE value it is more than that of the AT. So this is the condition we are getting it. Now other thing they are asking us is about the activation energies. So therefore this activation energy it is always either greater than or it is equal to the 0. Okay, so let us check this. AE value is greater than the AT, and either of the conditions where activation energy is greater than 0 or it is equal to 0, right? So here in the first option it says AT is more than that of the AE, so this is the incorrect. Second, it says EA is negative and AE is more than that of AT. This condition it is okay, but EA it is less than 0, it is saying it is not possible. Activation energy for this process it is always either gonna be greater than 0 or the equal to 0. Okay, third one, it is saying activation energy is 0 and AE is greater than the AT. So this is the correct one. One of the condition of the activation energy is being satisfied and other is AE is greater than that of AT, right? Next is EA is greater than the equal to 0 and AT is greater than the AE. So this is AEAT and AE inverse relation has been given. So this is the incorrect one. Okay, so this is how this question was to be solved. Next one is this. It says that in a photochemical reaction, 2.5 millimoles of A is converted into the B on irradiation with the 100 watts light of the wavelength 300 nanometers for 66 seconds. What is the quantum yield? So the quantum yield, we define it as, it is the amount of the reactant dissociated, amount of reactant dissociated dissociated to the amount of the photons, amount of photons. So now amount of the reactant that is dissociating, it is given that 2.5 millimoles of A is converted into the B. So this value, it is 2.5 into 10 to the power of minus of 3. Right, now this amount of photons we have to find it out. That is gonna be equal to amount of the energy observed upon the energy of the 1 mole of 1 Einstein, 1 mole of photon, or 1 Einstein or 1 mole of photons. That we can find it as, this will be energy observed upon the 12 upon the wavelength that is in the centimeter. Right, now E observed is, now power value it is given us as 100 watt, which is 100 joule per second only. Time span it is of the 66 seconds. Right, and upon the 12 upon the wavelength, which is given to us as 300 into 10 raised to the power of minus of 7, that will be in the centimeter. So this per second will get cancelled, and this value of the energy you will be getting in the joules, and this joule it will get cancelled out. So from here we can find the number of the, or the amount of the photons, and take its ratio with the amount of the reactant that dissociated will give us the value of the quantum yield. Right, so on solving this, the number of photons we will be getting it as 0.0165. This is gonna be the photons. So the quantum yield value, it comes out to be as 2.5 into 10 raised to the power of minus of 3 upon 0.0165. That comes out to be as 0.15. So this is gonna be the quantum yield value. The option B, it becomes the correct answer. Okay, next is this one. The rate law for this reaction, which is N2O2 getting being converted to 2NO, is first order in the concentration of N2O2. If the initial concentration of N2O2 is 1 mole per decimeter cube, the expression for the time dependent behavior of the concentration of the NOS. So how is the reaction proceeding? We are having is, this is N2O2 giving us the 2NO. At time t is equal to 0, you will be having only the initial concentration of N2O2, and this formed is negligible. After the time t, this is gonna be A naught minus of the x, and this is gonna be 2x. Right, now the initial concentration value, it is given to us as 1 mole per decimeter cube. So A naught value, it is 1. So the concentration of the N2O2, it will be 1 minus of the x in this case, and this is gonna be 2x only. Right, now the reaction, it is following the first order kinetics with respect to the N2O2 concentration. This is given to us. So according to the first order, we have A is equal to A naught times e raised to the power of minus of kt of it. Now the remaining concentration, which is A naught minus of x, this is equal to A naught into e raised to the power of minus of kt of it. Right, this is 1 minus of x, this is equal to e raised to the power of minus of kt of it. So from here, the x value we are getting it as 1 minus e raised to the power of minus of the kt. This is this x value. So that means the concentration of the NO, it will be equal to, it was 2 times the x, that is gonna be 2 times 1 minus e raised to the power of minus of the kt. So this is gonna be the value of the NO as a function of the time. So the answer, it becomes the option 1 in this case. Okay, I hope it's clear. So this is first order with respect to the NO. It was there N2O2, so that we have all substituted, and from that this X value we got it, and at time t is equal to t, 2x amount of it you were having, so that is you are getting the answer. Okay, so this was the last question that was from your chapter, which was the kinetics. So from the year 2011 to the year 2025, all the questions of this unit we are done with this. I hope all the questions that we have discussed are clear to you, but if you still have doubted any of the questions, that you can ask me in the comment section. I'll surely reply to that. And if you have understood the concepts, then make sure you hit the like button for the video and share it with your friends as well. And do let me know in the comment section how was this discussion, and next chapter which one you want to learn it, that we can start it. Okay, so thank you so much for watching. I'll be meeting you in the next video now with some new topic. Okay.